Okay, there's a bit more to say about chapter 28 and then maybe some of 29. Let's see what we can do. First of all, recall we had last time learned Faraday's law that when you have a changing magnetic flux, that induces an EMF and therefore a current. So I think I'll write that this way. I'll say that the EMF that's induced is equal to, we'll parentheses minus sign there, change in flux with respect to time, or if you like, negative ddt of NB, that's an A, NBA cosine theta. And the context, of course, was that you have a coil or some kind of loops of wire in the end of them, and there's a magnetic field strength B sticking through them. They have an area presented to that field of A, and theta is the angle between the perpendicular to the surface of the coil, the plane, the soap bubble film, you might say, and the field. So anyway, that's magnetic flux. The symbol, I need to put an M on it because otherwise you might think it's electric. They're magnetic flux. Notice it's a Greek letter phi or phi or whatever you call that. Magnetic. That's Faraday's law. And of course, what it does is it generates electricity. That's where we get electricity. Now, you can DDT the B by like externally controlling the magnetic field somehow. You could change A, that's that sliding bar on the rails thing. You can change N maybe in some weird way, like if you were quickly making a solenoid by wrapping up wire, I guess you'd generate a little bit of electricity if it was in a magnetic field. The most common thing is to change theta. It occurs to me, I didn't show you that, and I did bring some way away home to DDT some theta, some cosine theta. It's this. It's a genicon, it says, and it generates electricity. And this is a light bulb. And let's see if I can hold everything at the same time. Here we go. Whoa, it makes light. See, if I go slow, it doesn't make light. If I go fast, it makes more. What's really weird is by disconnecting, it suddenly gets easy. I'll show you that. Watch how easy it is. First, look how hard it is. Ah, so hard. I'm actually generating the electricity. Now, well, it's too easy. And then it's hard again if I stick it on there. So again, a generator, it's rotating a coil of wire inside this thing in a magnetic field. Now, the other thing I'll show you is I'm going to take that little generator and hook it to this generator. I've got generators all over the place. Let's see if I can actually do this. Connecting one generator to another generator. And skillfully, I will hold this one while that one's hanging there. Watch this. And then, there it goes. Oh, I got to go that way. See that? Wow. You know why? Because a generator is a motor, and a motor is a generator. They're really the same thing used in reverse. Let me quickly show you how that works. Say we have a, what do I want to do? Here's a loop of wire, and it can spin around an axis like, I don't like drawing these arrows. Yeah, it can spin around an axis like that, see? And it's in a magnetic field. I don't know which way. Oh, let's point the magnetic field up. And if I turn the thing towards you, I'm going to put a little towards you thing and an away from you thing down here to say which way it's going. If that's coming at you, we're going to get our little, I could use Lenz's law, the thing about the induced EMF is in such a direction as to produce a current that fights the change that produced it. But rather, let me just do this. I'll make my magnetic field point up, and here's my thumb pointing out of the board, and it makes this way. And so you force a current to flow like that, and you can figure out how much from that. That's a generator. Now, as it swings around, you notice once it gets to go parallel to the field lines, or in this case, anti-parallel to the field lines, you quit generating anything. Then once it starts going in, the current actually, in the sense of any given point on the loop, reverses. So it produces a alternating current. My goodness, we might just have to talk about that. But what if I do kind of the opposite? Switch cause and effect. What if I externally force a current to flow this way? And of course that way. And how would I do that? I would do it by hooking this thing up to a battery. Maybe over here, maybe it's connected, like mechanically connected, but there's some insulator stuff here maybe. And over here, I could have some wires that go to, a battery, and then the battery could make current flow that way. And if current flows that way, then you have a thumb and fingers, and it gets pushed into the board. Yes, it does. It gets pushed into the board, and the whole thing would start to rotate like that. Now, of course, there's two things you might notice. One is, if it ever reaches this point, the torque will be in the opposite direction, because if it ever gets down here, then this current's flowing this way, and that makes the opposite, and the thing would tend to just oscillate, wouldn't it? Even if it did keep turning, it'd twist up your wires, wouldn't it? Unless you're so smart as to invent, and somebody did long ago, many different kinds of these, called a commutator. Let me show you what that is. Look at this. This is so clever. You have your battery hooked up. It's got these little brushes. And then here you have the wire connected to like a semi-cylinder of metal, and there's another semi-cylinder of metal down here. I'm not sure how I'm drawing this. And there's just a narrowest little crack between them. I'm not sure I put the crack in the right place. Don't even look too hard. But as it spins, it forms an automatic current reversal switch, because when it rotates around in the correct position, the brushes will make contact with the other little metal semi-cylinder, and then you'll reverse the current, and the thing will keep running in the same direction, and that will be, of course, a direct current motor. It'll keep spinning the same way. So, look, motors and generators are really the same thing, using Faraday's law, or using the whole idea of a force on a magnetic, or a magnetic force on a current. Okay, enough said about that. The thing I have to introduce now is the last of the ANSYS that ORs have. I mean, like we had capacitance that capacitors had. And we had resistance that resistors have. It's time to talk about inductance, and that's what inductors have. So what does an inductor do? I guess it inducts, but reduces or something. What's the verb? Let's talk about that. So here's the thing. Now, if I am going to make some electricity, make an EMF, a voltage that drives current flow, I'm going to do that by DDTing some NBA cosine theta. I know that. But there's, you know what, I'm not sure the best way I want to say this. Tell you what, let me do this. Instead of talking in the context of a generator, let me just draw a coil. Yeah. It's a solenoid. In solenoids, we figured this one out. The solenoid has the flux through it. Well, I don't want to say this. Yeah, let's just calculate NBA cosine theta. So it's got an N, there's a B through it. There's the cross-sectional area of the thing. The cosine theta is easy because it's just one. So maybe there's a field through there. But why would there be a field through there? Well, there might be a field through there because there's a current running through it. Oh, that's weird. It would have a field through it because of the current running through it. Now, what's weird is it's going to like fight back on itself. You'll see how that happens. So this field that's through it is going to be because of its very own current. And the field in a solenoid was mu naught number of turns oh gosh, let's see. Yeah, times the area. I'm just talking about the B here. Trying to get this right. I think that's right. Mu naught times the number of turns. Yep, times the area times L. but I'm going to multiply it times the area again. I hope I get this right. I'm cheating just a little bit. See if I don't know where. Oh boy. I should have planned things better. Let me think for a second. Live or on video, and it's permanent. Okay. So here's your NBA. The B is due to the thing itself. It's mu naught times the number of things per unit length. Oh, no, silly me. It's times I. You caught me, didn't you? You caught me, didn't you? Oh, okay. Anyway, so times the A. Here's the thing. First of all, you can write you can substitute the little n for n over L. Sometimes the little n means the number of turns per unit length, in which case this becomes an little n times an L. All right, so that's another way to write it. And then I'm going to define this thing called inductance. It's equal to the flux, magnetic flux, divided by the current that's producing it. I haven't said this so brilliantly just yet. See, here's the idea. You're going to get a flux because of the current flowing through there, but it's a given that the more current you have, the more magnetic field you're going to have, and therefore the more flux. So this is a way of isolating the geometrical properties of the thing. You'll see what I'm doing right here. This is mu naught n, little n, the number per unit length squared, times A, times I, and I think, did I have another L somewhere? No, that's good. There's another L. Oh, the L's up top. Oh, because that's called in. That's called in. So anyway, I get that, and then I divide it by the I, as I'm supposed to, because I'm not supposed to be thinking about it's the I's fault. It's kind of like with a capacitor. You don't include the voltage of the battery in the capacitance thing because it's for a given battery you get a certain capacitance. Anyway, so I get this expression for the inductance of this thing. It's mu naught times the number of turns per unit length squared A L. And I'm pretty sure I did that. I did do that right. And what are the units of this thing? Oh, by the way, look at this. Notice how the number of turns comes in twice. It comes in twice because, first of all, the more turns there are, the more field there is. And then the more turns there are, the more they can respond to the field. So it's kind of both cause and effect in a way. And this is, again, the inductance of the inductor. It has to have some units. The units here are like Newton. Now, these are like newtons per square ampere. This is like turns per unit length. So, but the length is squared, so you get some square meters, but then there's some square meters up here, and then there's some meters. And by the time you do all this together, it's called Henry's. Yes, that's a last name. They didn't name this after somebody's first name. And I forgot the guy's first name. Anyway, somebody named Henry, and the letter, of course, is H, got honored with this inductance thing. He got inducted into the Hall of Fame. That's a bad joke, I'm sorry. So what do you do with this? What's it even for? Well, before I say what you want to use an inductor to do in terms of something practical, I'll tell you a demo that I didn't get to do because you're not here. It's also a demo, you kind of have to feel it. You kind of have to witness it directly. What I have is a great big bale of wire, a big coil of wire. It's got probably a couple thousand turns of wire on it. And typically I'll hook it up to a battery, and I'll have a couple of little alligator clips for a student to hold. And I have them do something simple, connect like 6-volt battery to this coil. It's just 6 volts. But when they connect it, it gives them quite a, kind of like that. See, it scared you. But anyway, I always had a student get addicted to this. Every time you hook it up, it does that to you. Every time you take it apart, it does that to you. I had a couple of students that just sort of like obsessively kept doing this, like, okay, that's bad imitation. But in any case, it gives you a pretty good little jolt. It ain't no 6-volt jolt. It's a pretty good jolt. So where'd all this electricity come from? I'll tell you, the same thing happens in your car if you have spark plugs. I don't know how these electronic ignitions work these days, but spark plugs, there was a coil. And it's only a 12-volt battery, but you end up producing like 40,000 volt sparks because of what I'm about to tell you. So here's how this works. If you have a solenoid, and of course it has, let's say it doesn't have a current flowing through it yet, and you start trying to make a current flow through it in the direction, I'm going to try to do like, this is the foreground, this is the foreground. I hope you get I'm not sure I drew it that way in the first place, but that's my idea. So I guess, no, I think I'll do it the other way. I'll have it come in here. So here goes the thing. Well, around there, this way, around back, this way. I think you see which way it's going. So what kind of a magnetic field is that going to make? It's going to make in the foreground here, my thumb goes this way and my fingers come up. Yep, it's going to make a magnetic field that points out the top. There's the magnetic field it's going to start to make. Fine, nice. But what if that magnetic field is increasing with time, which you almost have to do when you start from zero? If you're going to be anything, you have to start somewhere, okay? So if you start from zero, this magnetic field is now increasing as the current increases. But an increasing magnetic flux upward, according to Lenz's law, causes the thing to fight back and try to make an EMF, or try to make a current flow the other way from the increase. So an increasing current in this direction is going to automatically cause the inductor to get all upset and try to make a current that flows the other way. It might not win. It might not really make a current flow the other way, but it'll have the effect of slowing this one down, or at least reducing its rate of increase. It's going to fight. In fact, it's going to fight the change, which sounds like, I might have said that before, like Lenz's law. It's not that you fight a current flowing one way or fight a current going the other way. It's not that you're liberal or conservative. It's just you don't want anything to change. So no matter where you are, you fight the change. So an increasing current is going to yield this. It's called a back EMF because it fights back against the change. And it will try to produce a voltage that would really be such that down here where the current had been flowing this way, it would try to fight back, almost as if you stuck some shadow battery in this direction. And when students get shocked by that little thing, they're feeling that. They're feeling the back EMF fighting back, trying to oppose this change, and you just have to kind of get in the loop with it, literally. But what if I need to clarify. There was probably a battery pushing the current this way. This isn't the real battery causing the whole thing to happen. This is this ghost battery that fights back. Now, if I unhook the thing and this current starts to die down, there's still a flux pointing this way, but it's decreasing. And then the thing says, fight the change. I don't want a decreasing upward flux. So it would actually flip around and try to drive more of it. In other words, an inductor has the effect of tempering changes. It tries to oppose any changes. So when the current tries to go from zero to something, it says, whoa. And the faster it's trying to change, the harder it fights. And you can see that if I write Faraday's law this way, negative, that's Lenz's law saying fight back. And it's d magnetic flux dt. You got to remember the magnetic flux is Li. I just wrote L was flux over I. So this is Li. So it becomes E equals negative d dt of L times I, you can take the L out front, and then the operative thing, the thing you really care about here is the idea. We'll put yeah, okay, there we go. Oh, it's just, I'm going to write it this way. I like writing that way. I dot, d-I-d-t. There you go. An EMF produced by a rate of change of current. So the faster the current is trying to change, the more it fights back. And it works out beautifully so that, like, if you wanted to graph the current versus time, at first the current would like to change dramatically. In its attempt to get up to a final value, you know what? I need context. I think I need a resistor. I need a circuit. That's what I need. So what I would really have here, draw something new. What I really have is something like this. I'd have a battery. I'd have a switch. Yep, switch. And then a resistor, R. And then I would have my inductor. And look at the symbol for an inductor. You just basically draw a solenoid. Goes around the loops. And it has an inductance L. And the final current would be E over R. That's the current you'd think would happen in the first place. But the inductor won't let it, because when the current tries to instantaneously jump up to that value, the inductor fights back. At first, it fights back every bit as hard as the battery is trying and produces no current at all. But as the change slows down, so the thing calms down. You fight the change, but you kind of get used to it. So here's what you would generally expect. Yep, it's one of those, exponential sort of things like that, where the current gradually approaches a final value, but it suppresses the initial surge. They make surge protectors, don't they? I think maybe that involves that. In fact, I'll even tell you an application I made of this one time. I'm not sure if it helped, but I tried it. I used to have my old weather station on the other building. Now I have I don't know if you know, I had a weather station. This is a meteorology class. But I have a weather station up on the building, and it's radio linked to the room, and it's within range, and we get the radio signals. It shows what's going on outside. But I used to have one that was hardwired, and it was on the roof of the Carlos Science Center next door. And a couple of times it like fried the card in my computer because of lightning. Now, I'm not sure it was a full-fledged lightning bolt, but it was some surge, and it did that. So what did I do? I went up on the roof, and I got the wire, the cable, and I wrapped it many, many times around a metal pole, figuring I'm making an inductor. And then when a surge tries to happen and tries to crank the current way up, the inductor goes, no, 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 and it fights back. I don't remember if the problem ever happened again, and then it would get in the radio one, but at least it would try to help. Whether or not it was enough, I don't know. So that's one kind of surge protection sort of thing. There are probably other technologies. In any case, this is what you'd expect. So what's the shape of this curve? Tell you what, I'm going to use Kirchhoff's loop rule. Kirchhoff's loop rule applied to this thing looks like this. It goes, all right, I'll start here maybe. I go up E, I go down I, R. Then I go down across the inductor, but how much? Well, it's got to be a voltage. So I guess it's L di dt. It takes me back to 0. Your book does this properly, and I'll write the answer down in a minute. I don't feel like doing hard calculus right now, so let me pretend there's no battery. I know it wouldn't happen if there's no battery, but there could already be a current flowing or something. Generically, I just don't want to look at the E right now. So this would become L di dt equals negative IR. And then you go, well, I think I'll put the L on the other side, right? Is that what I want to do? Sure, I'll put the L on the other side. And then I get R over L, I, negative, and that's basically I dot, you might say. Well, I'll write it as di dt. Yep, di dt. And maybe you know that you can put that over here and this over there and say di over I know what to do with that, equals negative R over L dt. And look, you can integrate both sides because the integral d over I is a ln. And you can integrate over here to get t. Basically, you get that negative r over L times t is equal to ln of I. And you raise e to both sides, and look what you got. You get something like e to the negative r over lt. Now, to write it properly for the exact situation in hand with the battery in there, it ends up being, I'll make sure I don't write it wrong. It ends up being that the current is going to equal e over r times 1 minus e to the negative t over L over R. So that this L over R, you could call it tau. It's a time constant. It's the time to get to within 1 over E of wherever you're going. Like if you're decaying, remember like a discharging capacitor? A capacitor will discharge, and there the time constant is RC. We talked about that before. If you have a big resistance, that's going to slow things down. If you have a huge parking lot, lots of capacitance, then you're also going to slow down the time it takes to fill it. Look at the role this plays here. Longer times happen if you have apparently bigger inductors and smaller resistors. Let's brainstorm through that just a little bit here. Let's see. So why would it take longer to charge up if it's more of an inductor? That's easy. It fights the change more. More of an inductor, like with more coils wrapped up, that has more ability to fight changing currents. It produces more of a flux and more of a changing flux and more of a back EMF. So I'm not surprised that the tau has the L in the numerator, and that bigger inductances take longer times to get settled down in their equilibrium situation. Maybe not so obvious with the R though. Here the R has the opposite role that it does with a capacitor. With a capacitor charging up or discharging, you have the resistance slowing things down. Yeah, doesn't resistance slow things down? Not here. Here, a bigger resistance actually makes it take less time. Why would that be? You know what? If the resistance is bigger, then you're never going to reach as much of a current anyway, are you? And so it won't take as long to get up to 1 over E of it. Basically, it's like this. The resistance is reducing the amount of current anyway. And if it reduces the amount of current, it's probably also reducing, I hope I'm saying this right, or clearly, it also reduces the rate of change in that current, which means you have less of an effect that the inductor has to fight with. So yeah, bigger resistors mean there's not as much change to fight, because they don't fight as hard, and it doesn't take as long. Bigger resistors don't take as long. Now you've seen an RL circuit. Now, any real circuit in the world, even if it's just a wire that makes a turn a little bit, you've already got some inductance right there. So actual currents don't instantaneously shoot up to a final value, just because you flip a switch. Actually, there's a very rapid response, and it quickly levels off. Or if you put a big inductor in there, it takes a while. Now, so one reason you might do it is some kind of surge protection thing, but there are other interesting things. What really gets neat is when you put them in there with a capacitor too. This takes care of chapter 28, except that, you know what? Yeah, we're going to phase right into chapter 29. Yes, we are. Hang on. You see, inductors are not very interesting in DC circuits. They're like capacitors in those problems we talked about where, like, when you first flip the switch, it's like the capacitor's not even there, the capacitor, not even there when you first flip the switch because current's free to flow. But later, after a long time, then you don't get any current anymore. It's like the bridge is out. Inductors is the opposite. At first, it's like the bridge is out. When you first flip the switch, because the switch, it's like nothing can flow. Then later, after a while, it's like, never mind. It's just some roundabout way to go through some wire. Once the current reaches a stable value, there's nothing to fight. And so it's like a non-entity, well, it's like like just more wire is what it's like. So inductors play roles like that in circuits. Let me show you, well, first of all, let me point out that inductors are much more interesting in circuits which have a continuously changing current. And that's called alternating current, especially if you do it like this. You know, if you have like a current, you know what? It's probably the current. This is also a perfectly good map of the EMF. It's a sinusoidally changing EMF. In other words, you might say that E is not, you know, just some fixed value. It's you could call it E naught or the amplitude or something times the sine of omega t, where that's you know, the angular frequency there. That's actually 2 pi over the period, or if you like, 2 pi times the frequency. Yeah, it's the same thing. That's in parentheses. This is the kind of electricity we really use. Thanks to a big argument among some folks back a little over 100 years ago, about 120 years ago or so, famous folks, there was Thomas Edison, who wanted DC electricity, direct current, always flows the same way. There was Nikola Tesla and George Westinghouse, which were on the side of alternating current, where the current goes back and forth, back and forth. What in the world reason would you have for wanting the current to go back and forth, as opposed to just letting it flow the same way all the time? Well, you can generate it either way. There are tricks you can play, the commutator things. There's ways to get the electricity to go the way you want, you know, back and forth or direct. But why would you care? The answer mainly involves a thing called a transformer. And a transformer is something that transforms one voltage to another. I'm going to show this really quickly. So if you have, say, a iron hoop. I said iron because it's good if it has, you know, magnetic properties, so magnetic field lines kind of stick in it all the way around. And you come over here and you wrap some wire around it, like a few turns of wire, maybe I don't know, like 5 or 4 of them I just made. But over here you have like 8, whatever. Then if you put an alternating current in on this side, you go back and forth, back and forth, back and forth with the current, which is going to make a back and forth magnetic field that's going to be trapped in this stuff and go through the other thing over here. And when it goes back and forth, it induces or generates electricity on this side. But remember the role that N played. The bigger N is, the more electricity you're going to make. Remember, NBA cosine theta. So over here, if you have twice as many loops, you're going to get twice the voltage. It's an EMF that you're producing there, so twice the voltage on this side. Sounds like something for nothing, but it's not, because you're going to end up reducing the current by the same proportion. And since like P equals IV, you have a bigger voltage over on this output end, but less of a current. Now, is that something you want? You want less of a current and more of a voltage? I mean, they make the same power. You're not really getting something for nothing anyway. Yeah, here's the thing. When it goes out, like if this is your generator, generate your electricity in the first place, say alternating current, you're going to crank up the voltage over here. But if you crank up the voltage, look what you're doing. You are reducing the current, and P also equals I squared R. So the power lines that you're sending it out on have a given resistance. But if you, I'm hoping I'm saying this right. Yeah, if you have a smaller current, you're going to get a lot less power dissipated in the wire. I almost confused myself because I was thinking about the power that's trying to reach the ultimate end user. You know, somebody wants the electricity out there. They want their power. What you don't want is you don't want the power gobbled up by the resistance in the transmission lines. So by cranking up to a high voltage, you get a small current. And the small current, it's even squared. How about that? Saves hugely in the losses, you know, that you're going to have in the transmission lines, and you get the electricity to faraway users. Thomas Edison's DC was no problem if you were just running through about a mile of wire. Like if you had a power generating station in a city, a small city, or parts of, a few of them scattered around the city, like in New York, you could send electricity to customers out to like a mile away. Started to get out to 2 miles, it's kind of hard. They aren't getting much anymore because it's used up heating the wires. So Westinghouse said, hey, let's crank up to a high voltage, and then we can have a small current that doesn't have any losses, doesn't have great losses in the wires, and we transmit to people far away, even out on the farms, out in the countryside. And not just city folks are the only ones going to get this new electricity stuff. You're going to get it all over the place. And Nikola Tesla was in with him on that. That won out. Edison tried to fight it by, among other things, trying to like show how dangerous the high voltages were, and they are. But he like used his newly invented movie camera to make movies of various animals getting electrocuted, including an elephant that was bad. So said the zoo or somebody. It killed the trainer, I think. But anyway, so he actually did movies of deceasing animals using nasty alternating current electricity. That's a whole nother thing. You learn about that somewhere. I'll tell you what, this has now become a 36-minute video. I have a little bit more I'm going to say with the alternating current and so forth. I'll probably make one more of those, maybe another relativity one too. And we'll call that good. So enough for now. Bye.